It's going.
Why?
Do the chickens have large talons?
That's when they break the eggs, right?
Large talons. I don't understand a word you just said.
It's Napoleon Dynamite.
Yes.
Well, maybe I like Napoleon
It's
Dynamite.
somewhere between, that's the last time. I heard it's
Sorry, I
between,
didn't-
They did drink raw eggs.
it's somewhere between, so
Yeah, they did
you
drink
know.
right.
You know what I mean?
All right, we're on a new chapter.
What?
Huzzah!
Is it on, Ellie?
Mm-hmm.
It is?
It is.
Thank you for doing that.
I'm sure, like, if I get this 20%.
Okay, page 320.
Better in the code. The code really tells you don't do that. So I have to maintain the 3 And then I can maintain.
We want to now start investigating how stars die. What you're looking at is a dying star. This is called a planetary nebula. No, wait, that's a supernova remnant.
I don't think I'm this.
This is when a star exploded and released a bunch of stuff out into space.
Yeah.
This is a cat's eye nebula. This is a planetary nebula. This is at the center is what we call a white dwarf star, and all the stuff you see coming out is what was left of the star. What stars do when they die is they expand, and that's what our sun will do. Our sun will look like a planetary nebula in about 5 billion years. And so remember I said before, you have an inward, you have gravity pulling the star in, and you have fusion pushing the star out. And there's a balance between the two, and it ends up being a star of a certain size. More fusion, a little bit bigger. Less fusion, a little bit smaller. And stars continue to what they call burn their hydrogen, which just means fusing the hydrogen together to make helium. And slowly you're going to start running out of hydrogen, right? If that happens. And it happens slowly. Like I said, it takes billions of years. But this kind of describes what's going on. Most of a star, at the beginning of its life, is hydrogen, and a little bit of it's helium. But as we continue, in the core of the star, this represents the core. As you go to the right on this, you're getting farther and farther from the center of the star. So at the core of the star, the hydrogen is disappearing because it's turning into helium. Y'all understand this graph? A lot of you are staring at the floor. Not sure what floor has to tell you. Anyway, the core here is converted much of its hydrogen to helium, and there's very little hydrogen left. After 10 billion years, in the core of the star, there's hardly any hydrogen left. And there you see, at birth, after 5 billion years, after 10 billion years. So this is what is happening in a star like our sun. And so then, what happens? I'm purposely skipping all the words so I can explain this. So what happens is, at the center of the star builds up what they call non-burning helium ash. And when they say non-burning, that means that stuff cannot fuse. To get two hydrogen atoms to fuse takes a certain temperature. Do you remember what the temperature is? We already talked about it. To get two hydrogen atoms to fuse together, it has to be a certain temperature.
10 million.
10 million Kelvin. But to get two helium atoms to fuse together, it's got to be even hotter than that. It's got to be like 12 million Kelvin or 14 million Kelvin. And it's just not that hot, even at the center of the sun. So what's left is non-burning, that means non-fusing helium.
I thought the sun had some less 14 million Kelvin.
Okay, it might take hotter than 14 million. It might take 18 million to fuse hydrogen. Yeah.
Does the helium combine with other stars?
It will combine, yeah, if the star is bigger. And we're going to get it to combine in this star too. But not yet.
Is it before 14 million?
14 million K before, you're right. So it might take 16 million K to fuse hydrogen, to fuse helium. It doesn't, I don't have it there in the notes. There is a number though. So the it's all helium in the middle, and it's not hot enough to fuse the helium. It's still hot enough though to fuse the hydrogen, and so basically what happens is a hydrogen burning shell is fusing hydrogen around this helium core. And as the helium core expands, this hydrogen burning shell starts moving outward. So we're not just doing fusion in the middle of the star now, we're doing fusion further out. Because we're out of hydrogen in the middle. And so this hydrogen burning shell expands outward from the middle, because there's no hydrogen left in the middle, so we're burning hydrogen, we're fusing hydrogen further out, and it starts pushing the star outward. The fusion's not just combined to the very center now, it's moved outward. And when the star starts expanding, because the fusion is moving outward, it pushes the gases of the star outward, and the star starts expanding at this stage. Now the star's dying. And it comes off of the main sequence, and it starts getting brighter, and starts becoming what we call a red giant. It starts getting brighter because it's bigger. But since it's larger and takes up more area, it's getting cooler on the outside too. And so it goes to the right on the HR diagram. To the right means the surface temperature is cooler, and up means it's brighter because it's so much bigger. So it starts getting cooler and bigger. And thus we now have a red giant. And it might take 100 million years for it to expand and get bigger and bigger and bigger. This is what's going to happen to our sun. As when the hydrogen stops burning in the middle, the hydrogen that's fusing will start moving outside, and it pushes the star bigger, and it expands to become a red giant. If you were on Earth at that time, you would see, if you could live for 100 million years, you would see the sun expanding and getting bigger in the sky and being red colored.
But like it gets cooler because it's less dense, right?
Because you have the same amount of stuff taking up a larger area that makes it cooler. It's like spreading out your fire. It's going to not be as hot if you spread out all the burning embers. The embers are located in one spot. It's a lot hotter than if you spread them out. And so as the sun expands, it gets cooler and bigger, and it'll get bigger and bigger in the sky. In sunrise, right now the sun takes up 1 degree of sky, which is the size of your pinky nail at arm extended. But when the sun starts to expand into a red giant, it'll start taking up more and more of the sky. In sunrise, you'll see the sun covering 20, 30, 40 degrees of the sky as it gets bigger.
Will that impact us as far as
The temperature goes way up on the Earth. And the oceans will boil away, and the atmosphere will burn off, and all the life on the planet will die. Brutal. But it'll happen gradually over 100 million years. It wouldn't be one day you wake up and it's real hot. It'll just slowly get hotter and hotter.
Global warming.
Now, one cool thing in the process, as it's growing and expanding, and we're getting so much hotter that life can't survive here, Mars would be getting hotter too. And Mars is cold, so maybe Mars would get to the point where we could all move to Mars. Become Martians. Of course, this is 5 billion years off into the future, so who knows what it's going to be like. We might already be on Mars. So this is Arcturus. That is a red giant. And that's how big it is compared to our sun. And so it's way bigger than our sun. But our sun will eventually get that big. And when it does, it's getting ready to die. So, what's finally going to happen here is, remember, there's still gravity pulling in. And finally what you're going to have is enough helium at the center. And nothing pushing the helium out, only gravity pulling the helium in. And the helium that builds up at the center is not doing fusion, but gravity's pulling in on it, and it gets so massive, and it's pulled in so tight that the pressure builds up and it gets hot enough where it can start fusing too. And the helium can start fusing. And the helium starts fusing. I just read it there in my notes. The helium starts fusing at 10 to the 8th K. How hot is that? 10 to the 6th is a million. 10 to the 7th is 10 million. 10 to the 8th is 100 million K. So it's got to get, Kathleen, it's got to get to 100 million K before helium can fuse. And it'll do that in the center as more and more helium builds up and the pressure from gravity builds up. And then suddenly the helium starts fusing. And you get what's called the helium flash. Hold on, I'll come back to that. You see this point called the helium flash? At the helium flash, the star actually gets a little bit smaller and not quite as bright, and which you don't really know why that is. There are reasons that have to do with physics, laws of physics. And anyway, the star hangs out on this horizontal branch for a good while. Tens of millions of years. And so there are a lot of stars that are kind of spread out right about here on the HR diagram. And what it's going to do when the helium is fusing, helium fuses together and will eventually fuse together and make carbon. The same kind of carbon that makes up the molecules in your body. And the molecules of trees and all this, carbon starts forming in the center of the star. So we have a layer of carbon in the middle, helium over that, and hydrogen over that. The sun becomes layered like an onion at this point. The carbon in the middle can't fuse, but the helium around it is fusing, and the hydrogen around it is fusing too. What were you going to say?
I said ogres are like onions.
Ogres are like onions?
Because you said it's from Shrek. Don't worry.
Oh, that's from Shrek?
Yeah.
They have layers.
They have layers? Shrek's
Okay.
great. Aren't they making another Shrek?
No, they should stop.
They just made 4, and that's it. Because the 4th one was the last one.
It was right.
Okay.
And then they made Pussy.
I didn't see the 4th one. So it says the helium fuel lasts only a few tens of millions of years, burned up into carbon. The star expands again to become a red giant a second time, causing fiercer fusion of hydrogen and helium and expansion of the star. So basically your star's kind of going in and out as each time as a new layer lights up, it gets a little smaller. and then the fusion starts moving outward, then it grows again. And you end up going back up, and you get these giant, red giant stars near the top of the HR diagram that are cool on the outside, but very bright because they're so big. And hold on. And so what happens here is, let me go back to this picture. This hydrogen-burning shell here, as more and more helium fuses to form carbon in the middle, this hydrogen-burning shell keeps moving outward. As these two layers get larger, this layer keeps moving outward, and it pushes the gases around it off of the star. And the gases actually fly away from the star. So the fusion kind of moves outward and has some force to it, and all the gases around those layers come off. And so then you're stuck with something that looks like this. The gases on the outer layer of the star are being thrown away from the star. Gravity's not enough to hold them there. They're pushed away, and you get this like cloud of gases surrounding this white carbon core. And the white carbon core does not do fusion. But it's real hot because it's been in the middle of a star. I mean, it was at 100, it had stuff that was at 100 million K surrounding it. So it's a white, big ball of carbon. Did you know diamond is made of carbon?
Yeah.
It's almost like a big white diamond in space. It's called a white dwarf. It's white hot. And it'll take it billions of years to cool off. There's so much heat there. But it's not doing any fusion, so it's not creating a whole lot of energy. It's just hot. And it'll sit there in space as a white dwarf for hundreds of millions, billions, and even trillions of years. And eventually it'll cool off and you won't be able to see it anymore.
But it'll still be.
And then we call it a black dwarf. It'll still be there. A big ball of carbon. Theoretical physicists say that it won't cool off for trillions of years. And the universe is only 13.6 billion years old. So there are no black dwarfs in the universe yet. It is a theoretical thing that will eventually happen. But there's no way to see any of them because not that much time has gone by since the universe was born. So the gas is thrown off in all different directions and you make this cloud. And an ancient astronomer was looking at these and was saying, what are these? When telescopes was first invented, he was looking through them and he said, they look a little like planets. And so he called them planetary nebulas. But a planetary nebula has nothing to do with a planet. It's just gas that has expanded as the star dies. And look how pretty they are. In this one, the gas is just kind of expanding out to the sides. And they're not sure why that happens, but maybe it's because there's another star, a companion star, going around that star like this, making the material shoot off perpendicularly. And this one right here, did you see in the video? They don't think that that's a nice perfect sphere. Do you remember what they said in the video they think that looks like?
A cylinder.
A cylinder that just happens to be facing us. Like if I was holding a tube of a cardboard tube that holds wrapping paper or something. Toilet paper. It just happens to be facing us. If you turned it around this way, it would be long. That one right there. So these are this one's called Abel 39. This is called the Ring Nebula. This is called the Cat's Eye Nebula. That's probably the most famous. Looks like a cat's eye.
How does it look like? Oh, I see it.
I don't know. Can you say it?
Yeah.
And this one is M29.
I like it.
What a beautiful name.
Gorgeous.
We have no sound because my sound is on?
That
Yeah,
sounds
my
about
sound
right.
is on.
Hear it? Sound on the left, line left.
Oh, so it does have sound? Why is that not working? It's not working. Won't let me do it. That one let me do it. Just doesn't have any sound. So you're going into it here, and you see that's the white dwarf in the middle. That's your big diamond, your big ball of carbon. Hot, but not doing any fusion.
Dumbbell-shaped bipolar nebula forms in a double star system when one member expands and engulfs its companion. This creates a thick disk that constricts the outflowing stellar envelope, forcing the gas to escape along narrow lobes above and below the disk. Such a dumbbell pattern is seen in many planetary nebulae.
So for some reason, because it has that other star going around it, it doesn't spit gas out the sides, only perpendicularly to the orbit of the other star. And so you'll be left with a white dwarf there. And some other star going around it. Death of the Sun, Part 1.
Is an animation of the death of the sun from a faraway perspective. As we zoom in, time passes and our sun evolves. In nearly 5 billion years, our sun will change into the giant red phase, eventually ending its normal nuclear burning cycle. Its core will contract, all the while its atmosphere expands. Some of the terrestrial planets will likely be engulfed. What is left is a white dwarf star in the center of a burned-out planetary system.
And what would probably happen to the inner planets like Mercury and Venus is all of this gas and stuff, as the sun expands, will slow them down. Can you predict what would happen to the orbit of a planet if it was slowed down because it's running into a bunch of gas?
It would lose inertia and fall into the sun.
It would fall into the sun. So it would slowly start spiraling into the sun. Of course, that stuff is hot too, so it would completely burn the planet to a cinder. The surface would be all sterilized and burned up. If there were living things on the surface, they would be all burned. But you'd still have the rock itself. The rock itself could survive those hot temperatures. But it would be slowed down by the material, and it would start spiraling into the sun, and would eventually hit the core of the sun there. And the core of the sun is much more hot and massive than the planet, and so it would just be absorbed into the core. There would probably be a huge explosion of fusion when it hit, too. That would be interesting to watch. That's how our sun dies. Part 2. Here's part 2. There's more.
The sequel.
This is an animation of the death of the sun from the close-up viewpoint of planet Earth. The evolution of our main sequence sun to its red giant stage would cause the daytime sky to change dramatically. Earth itself would also greatly change. The oceans would boil, the atmosphere escape, the land would burn, and life would end.
Look at the little futuristic house.
What is very sweet?
It's a little nub
Is
house.
that a yurt?
It's a house shaped like an egg.
It's like Teletubbies.
The sun killed the
I
Teletubbies.
feel like that's Santa.
Marks on
Oh,
my head.
I watched those
Marks
shows.
on my head.
I
Leave it there, Mom, I'm watching Teletubbies.
They live in like a dome type thing.
Yeah.
This thing.
That baby is
Whoever made that show was seriously on drugs. It doesn't make
Like
sense.
the vacuum.
You guys remember the episode where the vacuum
I
like eats
was
a cookie and then it goes insane?
Thor.
That-
Look how big the white dwarf is. The white dwarf would be about as big as the Earth.
It's Will.
It's a real sun.
They're showing how it cools over billions of years and eventually becomes
I can't. I know it's too
red and
Like my grade.
still hadn't disappeared.
That's why I couldn't find it.
No, can't see
I
it.
already applied anyway.
The core of the dying star is extremely dense. The free electrons floating around in the core are compressed by gravity into a tightly packed ball that can pack no tighter. A golf ball size amount of this mass would weigh as much as a fully loaded tractor trailer. This tight ball of mass is called a white dwarf. And on the HR diagram, after it becomes a red giant and the red giant throws off all that material, it suddenly gets a lot dimmer. And so, this is the planetary nebula phase when all that gas is coming off of it and it's still glowing and it's still pretty bright. But when that gas gets far enough out, it cools off, loses all its brightness, and you're just left with the white dwarf that's not very bright at all because it's so small. It's also not doing fusion. It's not creating new energy. And then it'll slowly go from white to yellow to red and then eventually to black. So on this HR diagram, the star comes in like this, it sits here for billions of years, jumps off, and curls around. There'll be questions on the test all about this HR diagram and where is it on the diagram the longest, and point out the location where it would be if it were in the red giant phase, for instance. That's top right. You could imagine I could say, where on the HR diagram would you find white dwarfs? A top right, B top left, C bottom right, D bottom left.
Bottom.
Left.
Yes.
Where on the HR diagram would you find a very cool, large star?
The bottom.
Very bottom right.
Bottom right.
Cool, large star?
Just kidding.
Cool is right.
Bottom left.
Large is top because large stars are brighter.
Top right.
So that'd be top right.
Top
See?
right.
Trillions of years from now, when a white dwarf star has completely cooled, where would it be located on an HR diagram?
Bottom right.
Bottom right. Right over here. You see? Where is the sun located on an HR diagram?
Middle.
7.
Middle. Or maybe one of the choices will be main sequence. This is called the main sequence. So HR diagrams pretty useful in describing things. Are you serious, B? Sirius B.
That stands for Sirius Black.
That's that's a white dwarf star that's orbiting another star.
Sirius Black.
These two stars were orbiting one another, and this one died and expanded and got rid of all its stuff, and now it's just a white dwarf. This is called Sirius A. It's still a regular star. It hasn't died yet. What will this system look like after Sirius A expands and dies? It'd be two white dwarfs orbiting one another. And we see this kind of thing out there in space.
I have a question.
Okay.
Yes.
So, you only go up to carbon, which is like relatively high on the periodic table. How do they even make those things like
Things higher than that come in supernovas. And that's tomorrow. We're going to talk about supernovas tomorrow.
Alright.
You need a much bigger star to make larger elements than carbon.
Light.
But when stars get about 10 times as big as the sun, at least 3 times as big as the sun, and up to 20 times as big as the sun, you can make all the bigger elements because there's more gravity. And you'll be pulling that carbon in even tighter, and the carbon will start to fuse and form even larger elements. And they'll start to fuse and form even larger elements. And all the other elements in the periodic table are formed this way. But most of the carbon around probably formed in a star like our sun. So your molecules in your body are made of carbon. They came from the inside of a star. Your skin, this skin is made of mostly carbon, and that carbon was once in the middle of a star.
We're all made.
Carl Sagan has a famous line, "We are all star stuff."
So
That's where
Brad
everything
Pitt
came from.
isn't the only star.
What's that?
So Brad Pitt's not the only star. We're all superstars, guys.
You know what that is? It's a white dwarf. Do you get it? Do you get the joke?
Looks more like a white gnome.
You take my black finger. Right?
Yeah. What happened?
I got another video that we're watching. Extreme astronomy.
Sounds exciting.
Sam, do you like extreme sports?
No, I haven't.
Here's
I don't want
extreme
to.
astronomy.
There's a good chance that the unfortunate passengers inside this ambulance are on their way to the X-ray lab. Since X-rays were discovered about a century ago, this odd form of radiation has helped doctors pinpoint the damage and speed the recovery of thousands of accident victims. But X-rays have other uses, some of them a long way from your local hospital. New technology has enabled astronomers to take X-ray pictures of the sky. Working at the high end of the energy range, scientists are uncovering a universe full of unexpected wonders. They found